Hey, flipped geometry, how you doing? It is time for another flipped lecture. We're going to be in section 2.5 today of Bob Jones University's Geometry 4th edition, and we are going to set our foot firmly into the river of proofs today. So, yay! Good job. We've made it this far, and I know that you'll find it joyful, as I have. Actually, I really have. I really enjoy proofs. It's a logic puzzle, and they've always been fun for me to figure out. So I hope you see them the same way. Let's go ahead and get started. The first thing we need to do is review some categories of numbers. This is from Algebra 1, and you should be able to recall these things. A natural number is a number that you learned how to count with as a kid. 1, 2, 3, 4, 5, etc. They are whole numbers. There's no decimals. There's no fractions. They're positive, and they're greater than 0. Okay. Whole numbers is a very similar set. Whole numbers are natural numbers, but it also includes 0. 0. 1, 2, 3, 4, etc. An integer is also a whole number, but it can be positive or negative, right? So 0 and then plus or minus 1, plus or minus 2, plus or minus 3, etc. These are the kinds of numbers that you work with all through grade school. You met negative numbers later on in elementary school, but it's the same idea, right? These are all numbers that you've used before. We just have to identify the category that these numbers fall into. In addition to these regular numbers, we also encounter some not so regular numbers that you learned about also later in elementary school and in middle school. And these have to do with rational and irrational numbers. So a rational number is a fraction. And this expression is kind of confusing, but it's symbolized by this funny looking Q. That's a rational number. I don't know why Q means rational. I guess it's because R means real, but anyway. Rational questions, and it's essentially a fraction, p over q, such that p and q are elements of z. In other words, they're integers, positive or negative numbers, whole numbers, okay, but positive or negative, and q is not equal to 0. You can't have a 0 in the denominator. That's undefined, right? So some number over some number, and that is represented by q. That's a rational number. Irrational numbers is the complement of that. Anything that is not able to be expressed with a quotient or with a fraction. And so this would be numbers that are some decimal value that doesn't lend itself to being expressed as a quotient. Non-repeating, non-terminating decimals. So like pi, for example, 3.1415, and off it goes, right? And it never repeats and it never terminates. That's an example of a irrational number. Certain square roots don't repeat and don't terminate. And so like radical 7, you just leave it as radical 7. That's the best you can do. And that's an irrational number, okay? Both rational and irrational numbers make up the set of numbers called real numbers. So real is a fancy R, and this is all possible decimal values. Okay, now what would then be an unreal number? Well, those are imaginary numbers, and you'll get to that actually in Algebra 2, I believe, with I, and that's in the square root of -1. It's not actually a real thing. You can't square root -1, but it serves its purpose in certain equations. So all possible decimal values that are real numbers, and then if you can express it as a decimal only but not as a fraction, then it's an irrational number, and rational numbers are anything that can be expressed as a fraction. Okay, so those are some of the sets of numbers. Here's just a graphic to help you keep it all together. These are all real numbers. That's the universal set. They're either rational or irrational. Among the rational, you can have integers, which is 0 and positive or negative, 1, 2, 3, 4, 5, etc. You could have whole numbers, which includes 0 and 1, 2, 3, 4, but not the negatives. And you can have natural numbers that does not include 0, 1, 2, 3, 4, etc. Okay, so these are the sets of numbers that we'll be working with in this class, and you'll need to be able to identify a number as belonging to a particular set in your classwork later on. The next couple of slides are really important to make sure that you get this information down and highlight it in pink, circle it, put happy faces, put stickers, flag it in your notebook. You're going to be coming back to these next couple of slides all the time, or put a dog ear on that page in your textbook so you can find it easy. This is very critical information for you. We're going to be looking at real number properties. So the identity property of addition is that any number plus nothing is itself, or any number times 1 is itself. That's the identity property of multiplication. You will need to have that handy, right? The inverse property of addition is that any number plus its inverse is 0. So 1 plus negative 1, right, is 0. And the multiplication inverse property, the inverse property of multiplication, is that any number times its inverse is 1. A times 1 over a, 3 times 1 over 3 is 1, right? As long as a is not 0. The commutative property of addition, a plus b is the same as b plus a. Doesn't matter what order you put these things in. A times b is equal to b times a. Does not matter what order you put them in. The associative property of addition, a plus b, quantity plus c equals a plus the quantity b plus c. So it doesn't matter where you put parentheses. Grouping of addition does not matter. Multiplication, same thing. The associative property of multiplication, a times b, quantity times c, is equal to a times the quantity b times c. So it doesn't matter where you put the parentheses here either. Now, for subtraction, subtraction is not commutative, right? And division is not commutative or associative. So you've got to make sure that you're only doing this with addition and multiplication. The distributive property, a times the quantity b plus c, is the same thing as a times b plus a times c. Okay, so all of these things are properties that you've learned before. This is not news to you, but you will need them all the time going forward. So make sure that you have this. Okay, an equivalence statement. This is a relationship that is reflexive, symmetric, and transitive. If something equals something else, then an equal sign means that it is reflexive, symmetric, and transitive. What are those words, please? Well, let's help the brother out, right? Reflexive means that it equals itself, and that seems really stupid, but you'll be amazed at how many times you'll need that property, that this is itself, okay? Jason equals Jason. You equal you. Anything equals itself, okay? That's the reflexive property. The symmetric property is that you can flip things around on either side of the equal sign, just like you can change things on other sides of a plus or a multiplication symbol, and it means the same thing. Equal signs are the same way. B equals A and A equals B, right? Transitive, that if something equals something else, this second thing could also be equal to something else. And that means that the first and the third are equal to each other. So if A equals B and B equals C, then A equals C. Okay, and you'll use that all the time in geometry. This equals this. Oh, I know that that also equals this. Oh, that means that this thing and this thing are the same. Okay. Addition, the addition property of equality, that if A equals B, if they're the same, then you add C to either of them, you get the same thing. A plus C equals B plus C. That's the addition property of equality. You'll use that all the time. The multiplication property of equality, that if A and B are the same, then AC is equal to BC. You're multiplying both of them by the same value. Okay, so you will do this all the time in proofs, not only in geometry, you'll use these in algebra proofs as well. All right, so these are some very critical things. Make sure that you got that. If you have any questions, we'll go over them tomorrow in class. Moving on, the substitution property, that if A equals B, then A can replace B in any mathematical statement. And again, you'll use this all the time in geometry. So if you have these two things that are equal, you can take one out and replace it with this other one, and the meaning hasn't changed, right? It is still the same thing. So we can look at that with several examples. The trichotomy property, for any two real numbers, A and B, exactly one of the following is true. Either they are the same, A equals B, or A is less than B, or A is greater than B. You can't have both, A equaling B and A being greater than B. And that seems like, well, of course, but it's going to be necessary in proofs later on to understand that if I've said that these two things are equal, then they're equal. They're not greater than one or the other. Okay, So these are some properties that you will use that you need to have in your tool bag. So let's look at an example here. Name the property that justifies each statement. If 5s equals 60, then s equals 12. Well, that's a simple algebraic statement, and to find s, you would just divide both sides by 5, right? To isolate s by itself, you divide both sides by 5, and that would give you the answer that s is 12. But what did you do? Well, you used the multiplication property of equality. You multiplied both sides by 1 over 5, right? When you divide both sides by the same thing, you don't want to say the division property of equality. You want to say the multiplicative property of equality, because the property works better as a multiplication statement than as a division statement. And division is really just multiplying by the inverse. So 1 over 5 is the same as dividing by 5. Okay, so that's an example of a logical step that you might need to do, and then you need to identify what you did, the multiplication property of equality. Okay, name the property that justifies each statement. If p minus 7 equals 10, then p equals 17. And again, in algebra, you learned you just add or subtract the same thing to both sides. So here, if we're getting p by itself, we add 7. We add 7. What did you do? That's the addition property of equality. Okay, you added the same thing to both sides. Name the property that justifies this. 2x plus 3 equals y, and y is 5x minus 7. Then you could set those two statements equal to each other. 2x plus 3 equals 5x minus 7. Wait, what'd you do? Why'd you do that? Well, this is equal to y, and y is equal to this. So if a equals b and b equals c, then a can equal c. Okay, what is that again? That's the transitive property of equality. Okay, you could also call it the substitution property. Usually, both terms are equally fine. Okay, let's do a couple more. Name the property that justifies this. If 4t minus 1 equals u, and t equals 8u, then 4 times 8u minus 1 equals u. And you are confused. No, you shouldn't be. Here, look, this is a t, and we were told that t is this. So I can stick this in for t, and I get this statement. What did I just do? That's the substitution property. You could also say transitive if you wanted to, but substitution is the best here. I just took something, and I stuck it in there where the other thing was. Okay, and I now have a new statement that I can continue to follow. Okay, so proofs. Here we go. Put your big boy pants on. We're going to get into proofs. A proof is a system of reasoning or argument to convince a person of the truth of a statement. You are demonstrating that something is absolutely true. Now, remember, we assume certain undefined terms. We have lots of definitions, right, that are good descriptions of something. And then we have a system of axioms or postulates that you don't need to prove, because you can just see that they are in fact true, self-evidently true statements. And then there are things called theorems. Theorems are not self-evidently true. You have to demonstrate the truth of them. And you do that through proofs. So you are going to be building and working with proofs from now until the time of the Lord's return, as long as you keep studying and doing math in your life. And a proof is going to be the way that we can get to a theorem, that we can demonstrate that a theorem is in fact correct. So let's do one of these proofs. If negative 3 times x plus 6 equals 6x, then x equals negative 2. We're given this proof, and we're going to try to find that this is the answer. Okay, now this is an algebraic proof. This is not geometry yet, but we're going to be learning how these proofs work, and then we're going to apply them to geometry. You've probably already done some of these in your algebra classes. We're just going to be reviewing this logical formula and applying it to geometry in a moment. So here is a proof. This is what it looks like. Okay, the formatting is important. It's 2 columns. On one column we have statements. On the other side we have why we can make that statement. If you have the right statement but the wrong reason, you're wrong. Okay, if you're skipping steps and you have not demonstrated every step of the process, but the steps that you have demonstrated you have the right reasons for, you're wrong. So proofs need to be step by step, small steps at a time. Don't assume or skip anything. Okay, so Negative 3 times x plus 6 equals 6x. That's a given. We were provided this in the question. Okay? So now what I'm going to do is I'm going to distribute the negative 3 times this quantity. Negative 3x minus 18 is what we get when we multiply both of those terms by negative 3. That is the distributive property. So see what I've done here? I've identified why I can do that. Don't just say, oh, you multiply across. No. Tell me why. Okay? Now I have negative 3x and 6x. I'm going to add 3x to both sides. That's the addition property of equality. Negative 3x plus 3x is just now negative 18. And 6x plus 3x is now 9x. Okay? So I have negative 18 equals 9x. That's, you can just say simplification. I'm doing math. I'm doing math now, right? This was the addition property of equality. That's why I added the same thing to both sides. Now, 1 over 9 times negative 18 equals 1 over 9 times 9x. That's the multiplicative property of equality. And feel free to abbreviate as you've seen them do here. I'm multiplying both things by 1 over 9, which is going to get rid of this term, right? 1 over 9 times 9x equals x. 1 over 9 times negative 18 is negative 2. And I just simplified. I did math, okay? X equals negative 2, symmetrical property of equality. I flip it around so that it's more logical. X equals negative 2 instead of negative 2 equals x. So every little thing is shown. And why I can do that is delineated. Okay, and this is a proof. And you will do these kinds of things a whole bunch. Let's look at one more example. Given the figure x, y, z, so that means that they're collinear, and xz equals 35, solve for b and justify each step. Okay, so I have this number line, and I've been told that x to z is 35. And I have an algebraic expression here for this portion of it, and another one for this portion of it. And I know because of the betweenness that this plus this has to equal the whole. So I'm going to do a proof here. And again, statements on one side, reasons on the other. Okay, so here's my statement. And my first reason is that it's given. X, Y, Z is collinear. XZ equals 35. I was given that. Okay. Now, XY plus YZ equals XZ. I am just identifying here that one part of this segment plus the other part of the segment is the whole segment. And that is the definition of betweenness. The definition of betweenness. That if Y is between X and Z, then this is true. Okay. Now, I'm going to say that XB is the same thing as this, and YZ is the same thing as this. And I've gotten that from the figure, right? So from the figure, I just took these two algebraic expressions, and now I'm putting them in for their segment names for X, Y, and YZ. And this is what? This is substitution. Okay. Now, I can combine like terms. 4b and 7b is 11b. 3 minus 1 is 2 equals 35. And here I combined like terms. This is just doing math, simplification. Okay. Now I have 11b equals 33. What did I do? I subtracted 2 from both sides. And when I did that, I added negative 2 to both sides. I added the same thing to both sides. That's the addition property of equality. Okay. Now I'm going to get b by itself. I'm dividing both sides by 11, or you could say I'm multiplying both sides by 1 over 11. That is the multiplicative property of equality. Okay, and then I have my answer. Okay, b equals 3. So those are some examples of algebraic proofs. We will very shortly apply them to geometry. Let me know what questions you have when we see each other tomorrow in class. Until then, God bless you. Jesus loves you, and so do I. I'll see you tomorrow.